Alright, so far for circuits, we've done the math for series, resistors in series, and we've done the math for resistors in parallel. So you have everything that you need to be able to approach a circuit that looks like the one below. So something with both parallel and series. So this parallel section is in series with this single resistor. So let's take a look at this example and follow just 2 steps to figure out its total resistance. Long steps, but still only 2 of them. So first thing we're going to do, number 1, determine the equivalent resistance of the parallel part. So we have to turn these 2 things into one thing before we can start to worry about the series part. So we already know how to do calculations for parallel, so let's just jump into it. 1 divided by our equivalent resistance is equal to 1 divided by, let's see, what do we have in parallel? 24 ohms and 8 ohms. So when we do that math, we get 0.167. And remember, it's the inverse of ohms. So if we want to figure out the equivalent resistance, all we have to do is invert this, 1 over 0.1667. So the equivalent resistance that we get out will be 6 ohms. So really all we're doing is saying, hey, let's take out these 2 resistors, and what could we put in its place to make it not change? So we're taking out the 2 parallels and putting in just one single 6 ohm resistor. So now that we've made that change, we can change our diagram a little bit to look like this. So we come out of the battery, we took out the parallel part and replaced it with just the single 6 ohm resistor. And we can see pretty easily now that it's in series with that 4 ohm resistor. So next step, treat the equivalent resistance of resistors in parallel. So this that we just did is a single resistor. We made that substitution. And calculate the total resistance by just adding up the series. So we have 2 different resistors in series. So equivalent resistance is equal to 4 ohms plus 6 ohms, just 10 ohms. So really that's all there is to it. Try to break down the parallel sections first, and then you just have a really easy series circuit. So example, same circuit we were just working with. So consider again the circuit whose total resistance we've calculated. What is the current through each resistor, and what is the power dissipated in each resistor? Alright, so let's figure out what is the total current. Well, we already know our, oh my goodness, our resistance, our equivalent resistance is 10 ohms. Looks like this diagram here should say just volts, not ohms. So to get a current, we do our potential divided by our resistance. And we get a total current of 3 amps. So since there's only one pathway for the current to flow through resistor 1, that means this has to be the current flowing through I1. To figure out the current through R2 and R3, it's a little bit trickier. We have to know what potential drop this parallel section causes. So what is the potential drop across 2 and 3? So we know the current going through there is 3 amps, and we know the equivalent resistance there is 10 ohms. Sorry, not 10 ohms, that's the total. If we're looking at just 2 and 3, that's only 6 ohms. So the potential drop caused here, 3 times 6, is 18. So this section uses up 18 volts. So now that we have that, we can figure out what's the current through each one. So the current flowing through 2 is 18 volts, and we divide by 24 ohms to get 0.75 amps. To figure out I3, we have 2 different ways we could do it. We could do Ohm's law and then check by adding, or we could add and check by doing Ohm's law. Either one should get you the same answer. I'm just going to do Ohm's law here. So 18 volts divided by only 8 ohms for 3. And we get 2.25 amps. Doing a quick check, 0.75 plus 2.25 does equal 3, so whatever goes in remains constant through there, so we're good. Last thing we want to do is calculate the power dissipated by each resistor. So the power dissipated by resistor 1 is going to be 3 amps squared, and we multiply by R, so 4 ohms. So 36 watts, P2. 0.75 amps squared multiplied by 24 ohms. .5 watts. And then our last one is P3. So 2.25 amps squared, and we multiply by 8 ohms. And then you can use your total current and equivalent resistance to double check that. So 3 squared times 10 is 90. If we add these up, yep, we're good. Alright, and that's where we'll end for today.